Welcome to today's webinar. Let's get started. Let's look at our agenda for today. Today we're looking at using Modbus TCP and Modbus RTU in an IEC 61131 programming environment. We'll start today with a quick review of Modbus. We'll look at the Modbus data model and their traditional Modbus implementation at Horner. We'll discuss the two different options in Cscape for IEC 61131 programming, which are Standard IEC 61131 and Enhanced IEC 61131. We'll talk about how those are different and why you would choose one over the other. And then for each of those two options, we'll talk about how to implement Modbus as a server on your OCS. We'll have demonstrations throughout and we'll finish with a Q&A session. We'll start with a quick review of Modbus. Remember, Modbus is the most common protocol that is used by industrial devices. So, if you have an application where you have industrial devices from multiple manufacturers and you want those to share data, Modbus is the protocol that is most commonly available. Modbus Data is available serially over RS-45 or RS-232, and then you'd use Modbus RTU or Modbus ASCII, which are Modbus serial protocols. Modbus TCP is used for sharing data over Ethernet with multiple industrial devices, and it's a client-server protocol. Modbus is modelled around a traditional PLC which consisted of two different types of data: Boolean data, which is 1-bit based, and integer-based data, which is 16 bits. Now, there are four different types of Modbus data. You have coils, inputs, input registers, and holding registers. So, coils are read-write bits, inputs are read-only bits, input registers are read-only registers or 16-bit values, and read-write integers are holding registers, and each are assigned addresses. As you can see on the far right there, those are their traditional 5-digit Modbus addresses for each of those four data types. Now, there's also a 6-digit scheme because as PLCs have gotten larger, they have more addresses than just 10,000 per section. So there's the 6-digit scheme that is sometimes used, but the 5-digit scheme is still more common. The first Horner PLC has been around since the 90s when all PLCs were register-based. With Horner PLCs, there were different types of memory. For read-write bits, we had Qs, which are real-world outputs. Ms are internals, but they're retained after a power cycle. Ts are internals that are not retained. There were also read-only inputs, which are real-world inputs such as %, which map well to input registers. And then we had different types of read-write type integer-based data, including real-world analog outputs, AQs, and internal integer data or %or. So, when we assigned a Horner address to a specific variable, it automatically got a corresponding Modbus address through a standardized map. This on the right is what a standardized map looks like. On the left-hand column are the traditional Horner address types. In the middle column, they are mapped in Modbus, and in the far right column, it shows the 6-digit address. 3 of the 4 available logic languages and Cscape still use this map, as does Standard IEC. If you're using advanced ladder, either register-based or variable-based, they also use this map. However, this map does not apply to Enhanced IEC. Standard IEC was the first variable-based logic editor in Cscape. It predates variable-based advanced ladder. Like every other IEC package, it offers the 5 languages of ladder, structured text, etc., which are listed here. It has been available for 10 years and is an extremely popular option. The way Standard IEC was implemented before was to take the IEC code in Cscape that was created by the applications engineer and compile that code into Horner's runtime codes that are downloaded to the controller by Cscape and that are executed by the OCS at runtime. So that's how things work with Standard IEC. Enhanced IEC has only been around for a few years. It was released as part of the 9.9 Service Pack 4. It's a licensed feature, so requires a modestly priced one-time runtime license for each OCS that's executing it. It offers quite a few advantages, for example, support for more than 50,000 variables and executes faster at runtime. It supports online programming and simulation and has advanced debugging tools, including the ability to do trace points, and it also has very good exception handling. One of the ways it is different is in the way it handles Modbus, but first let's look at the way Cscape and the OCS handle Standard and Enhanced IEC. In this diagram on the left, there are the 4 different logic languages that can be used in Cscape in any one application, but we'll focus on the 2 at the bottom. For Standard IEC, once it is created by the application engineer, Cscape then must do a code conversion before downloading it to the OCS. And on the OCS, that download is made to the traditional Horner runtime logic engine. However, Enhanced IEC has its own runtime logic engine that's existing on the Horner OCS, and so it can download its code directly. And that's how it has the extra capacity, the extra performance, and some of those extra features. Most OCSs today have both of those runtime engines available. So the XL series from the XL4 up, the XL Prime series, the upcoming Canvas series, and the RCCs all support both runtime engines. However, the Micro OCS does not support the Enhanced IEC options. So now let's cover a little more detail on the two different logic engines, starting with the Horner Runtime Logic Engine, which is used by all the languages except for Enhanced IEC. Because it is the traditional logic engine, it fully supports all Horner address types, and because of that, it can very easily use the traditional mapping method for Modbus server. However, with the Enhanced IEC Runtime Engine, it's variable based and there is no Horner address support, especially not for internals. There's no such thing as an OR or an M or a T in an Enhanced IEC. Now, we still have Is, AIs, AQs, etc., and S's and SORs for mapping purposes. You can take your variables and map them over to real-world I/O and system bits, but that's the extent of it. So, because of the fact we don't have all these Horner address types, we can't just use the Horner-Modbus Map. We have to use a unique Modbus server, but more on that later. Now we'll look at how to implement Modbus server with Standard IEC. As it uses the standard runtime engine, it can use standard Horner to Modbus memory mapping. We map the variables we want to share over Modbus to Horner or NDEM addresses because they will automatically have a corresponding Modbus address. So we don't directly map Modbus addresses, we map Horner addresses and then they come through with the Modbus map. For supporting Modbus server serially over RS-232 or RS-45, we use logic. It shows how to do it in ladder logic here in IEC. It could be done in structured text or one of the other languages as well. To enable Modbus as a server or as a slave serial device, you need to use these two function codes. The first one is OpenCom, which opens the communication port that you're going to use for Modbus, and it sets the communication parameter. For this function block with Standard IEC, when you enter in these parameters, they need to be constants. To finish the details for Modbus, there's a second block called the Modbus slave block. This is a block that requires you to name it, like a variable, and that the name is not the same as any other variable. This block allows us to set the Modbus address between 1 and 252 and the Modbus timeout in milliseconds, and that's the setup required for Modbus serial. Modbus Ethernet with Standard IEC is handled through the hardware configuration. You go to Hardware Configuration under the two LAN ports, press the config button for the LAN port you're enabling Modbus for, then you click the checkmark for Modbus slave, and then if you highlight that and press Configure Selected Protocol, which isn't visible here, then you have the ability to go in and change some details. For mapping, it is recommended to get your program variable list, and then for all the variables that you want to assign as Modbus variables, you go to the memory column in the program variable window and you assign them appropriate OR or M Horner addresses, which correspond to Modbus addresses through the map. Also, if you're assigning 32-bit variables, they'll take up 2 consecutive %OR variables instead of 1. Now it's time for our first demonstration. So we have an XL7 here that is running Standard IEC and is connected to an I/O simulator. There are some analog pots that are being input to simulate a pressure sensor and a level sensor, and then in logic it's being converted over to engineering units. And then we'll be assigning Horner addresses to all the data that we want shared over Modbus. In this example, it's strictly the engineering units for pressure, level, and then the set point for level. Those are the 3 things here on the screen. They're all OR type data because they're all integer type data, and by assigning them to ORs, they're automatically assigned to corresponding Modbus registers. Starting with the hardware configuration, we'll look at what we did to enable Modbus over Ethernet. So we go to the hardware configuration first, and then to LAN 1, the port we're using with this XL7. And under configuration, we had to configure all the normal Ethernet parameters, but then also selected Modbus slave. And because this is standard IEC, there's not much else to configure. You can configure selected protocol and change the defaults in here, but in this case, the defaults will work. Now we'll look at how to enable Modbus serial in logic. So what you'll see under the Modbus serial area in logic is that there is an assigned IEC ladder, which is where there are the OpenCom and Modbus slave blocks. Now we'll look at how to map variables to Modbus address space. There are 3 values in this example that we want to share over Modbus. The variable that has been converted to engineering units for pressure, level, and level set point. So we want to change these remotely. So we go to the program variable map area and find the variables that were assigned for pressure level and level set point. Here's a logic routine that is also written in an IEC ladder that scales raw data from the analog inputs for pressure and level. Again, in the program variable area, we scroll to where those 3 variables we want to share are listed. And then in the memory column, they're assigned a Horner address, which corresponds to a Modbus address. So here we have OR1 for pressure, OR2 for level, and OR3 for set point. We can see on the screen here when they're mapped in Modbus address space. Now we'll see if we can remotely read and change these over Modbus. To demonstrate reading and writing Modbus, we use a utility called Modbus Poll, which runs under Windows. As you can see, the data on Modbus Poll matches the data we previously saw on the screen. We can change the set point remotely and then can see that corresponding set point change on the XL7. So that's all for applying Modbus with standard IEC. Now let's look at using Modbus server with enhanced IEC, which uses its own runtime engine. This means we can't use the standard Modbus map with Horner registers. So we create up to 4 variable arrays in the program, and one each will be used for the holding registers, the input registers, coils, and input bits. We don't have to support all 4 types, we can just support one, in which case we only create one of those arrays, and we can match how much data we want to share with the size of the array. Similar to Standard IEC, we're going to use logic to enable serial Modbus slave and still use the open COM block, but can also make all inputs to that function block variables, making it a lot easier to change things at runtime. To enable all Modbus parameters, we have a unique function block for enhanced IEC called the Modbus Map slave. This is where our Modbus address and timeout are assigned, but is also where we specify the 4 different arrays that we've created for input bits, coils, input registers, and holding registers. Now we look at enabling the Ethernet version in enhanced IEC. So it starts out the same, but when we double click to configure the details, the dialog box gives the option not only to select Modbus TCP or UDP, but also to assign the 4 different arrays, the length of which are automatically assigned on the right, as Cscape automatically reads the size of the array and will show the size appropriately. So those are the configuration requirements for Modbus Server with enhanced IEC. To map variables to Modbus, we'll take the data and the variables we've created in our application, and then we're going to create logic that copies the data from those existing variables over to entries in the Modbus array of the appropriate data type. We can use structured text assignment functions, which take a pressure and a level and move those into the Modbus input register array. On the bottom right, you can see that we didn't use a simple assignment function for moving variable data into holding registers. This is because if you have read-write data that could be written locally or remotely, and you want it assigned as a holding register, then you need to have some logic that detects whether or not that variable was changed remotely. And if it was, then you need to change the corresponding local variable to reflect that, which simple structured text logic accomplishes. Now, for our second demonstration, we'll look at Modbus Server with enhanced IEC. Like the previous demo, we have an I/O simulator. We have raw data simulating a pressure sensor and a level sensor, and converter data that uses logic to convert the raw data to engineering units. It's all integer data, so even though we have a decimal point on the screen, the actual data in the register is 909 rather than 90.9. One of the differences here is that there is no Horner address assigned, and we also chose to use 2 different areas of Modbus memory for the data. So for the pressure and the level, which is read-only, we mapped them as input registers and 30,001 and 30,002, and then placed the read-write data into the holding register area starting at 40,001. Now we'll look at how we program this, starting in the program variable window in Cscape. This is where we created 4 arrayed variables that represent the data that we're going to share as coils, inputs, input registers, and holding registers. For the purpose of this demo, we have support for 4 coils, 6 input, 4 input registers, and 4 holding registers. Now we'll look at the Ethernet configuration through hardware by going to Hardware Configuration and then LAN 1. We configure selected protocol and put in the first member of each of the 4 array variables, which Cscape automatically detects the size of. So that's all that's required for Modbus TCP server. Now we'll look at the logic routine we use to enable Modbus slave serially. Here we've done that through a Modbus routine using the open COM block, but using the variables instead of constants. Then, using this Modbus Map function block, we used variables as well. And this is where we set a variable for Modbus address, timeout, and status, as well as assigning the 4 Modbus arrays. This is one of the function blocks that needs a unique instance. Now we need to assign a variable for mj3_Modbus, which is the instance of this function block. So if we double click and look at the list of available types, Modbus Map slave is one that is available, and so we enable it. Now we look at how we moved variables that we used in the application over into these arrays that we created, so that the Modbus data appears where we want it to be. So in this application there are a couple of different logic blocks, one called input map and one called output map. The input map can be used to map real-world data over to variables that are used in the program. So for the 4 digital inputs that are used in this example, we assigned a limit switch, a photo eye, a proc switch, and an e-stop switch to inputs %I, 1, 2, 3, and 4, which correspond to the real-world I/O array that's built into Cscape. Because it's an array, it has 0 base addressing, but as well as mapping real-world inputs, digital and analog, over to variable names, it can be used for mapping over any of the holding registers, and is also where we would put coil data. Now, here we need logic, which compares the current value of a specific Modbus holding register 0, or the first one, which corresponds to have address 40,001, and we're checking to see if that value was changed remotely. If it was, then the value it was on the last scan will be different or not equal to the value it was on this scan. In that case, we take the internal variable that is used with that address and copy the new remote value into that variable. Otherwise, we just take the value of the local variable and move it into that holding register. So that's some logic that we created using structured text for a read-write variable that could be written both locally and remotely. For output, it's easier when we're mapping Modbus data that is read-only, which means input bits and input registers. And for this, we can use simple assignment logic. For any Modbus addresses or variables that we want to share over Modbus, we just use the simple assignment statements. So for each array entry, we can just map over using assignment statements, the limit switch, photo I, proc switch, etc., which are read-only, as are the pressure and the level. Now, as you can see, we also mapped over a motor starter and a solenoid, which are physical outputs, but from a Modbus standpoint, they are read-only. Now, if we go back to the input routine, here we wrote this structured text routine. If we wanted to detect if the holding register had been written remotely or not, it required us to keep track of the last value of that holding register on the previous scan. We use simple logic in the Modbus ladder routine to move the current values of the holding registers and coils over to another array that we can compare next scan to see what the values were last time. Now we make sure everything is working properly using Modbus pull. We start by looking at the input registers, pressure and level. This time we've mapped those into Modbus input registers 30,001 and 30,002, and the data has an implied decimal point placed here using the Modbus pull software. So if we look at our OCS and see that we can change the data here and then back to Modbus pull, we can see everything is updating correctly. Now to look at holding registers, we must open up a different configuration of Modbus pull. Here it is showing the set point, which is Modbus register 40,001 with a value of 5,000. And if we go back, we can verify that is the set point, which we can change here, but we could also use the Modbus pull to change it. As you can see here, it's just as easy to change it on Modbus pull as it is to change it on the OCS. So with Enhanced IEC, it's all about creating those arrays of data for each of the 4 different Modbus register types. And remember, Modbus is based on registers or addresses. So that concludes our webinar for today. Thank you for listening, and the Q&A session will begin shortly.
Okay, let's have a quick look at the questions tab there now. I'm not seeing anything currently in. I'll give it another minute or two to give people a chance if they'd like to. So next week our webinar is on MQTT Sparkplug. So if you have any interest in that, please feel free to go and register now from the webinar page. Okay, there's still nothing in. Must have been clear. As usual, if you have any webinars that you missed or you'd like to go back on, they're all up on the website, so you can always go back and look at them. Okay, thank you all for coming this morning, and we hope to see you again next week.